Something like that. Greetings and welcome, friends. Today we're starting a brand new zone called polar coordinates. All right, so you've never heard of those before. And complex numbers. You've definitely heard of them. Those are the imaginary ones, or the hybrid part real, part imaginary numbers, right? So the polar coordinates is what we're going to talk about today. I've got a handful of little definitions here. The polar coordinate system is recording the position of a point using the distance from a fixed point and an angle made with a fixed ray from that point. Okay, so instead of having a rectangular coordinate system in which I'm kind of like marking points by over 2 and up 3, right, and I have over and an up, an x and a y, a horizontal and a vertical component to my ordered pair, I'm going to recognize the location of exactly the same point, but with a different means of doing it. So instead, I'm going to measure the distance that that point is from the origin, and I'll call that r, and the angle that that distance is from my positive x-axis, so to speak, which we'll refer to as the polar axis, as indicated here. So it turns out I can refer to this point as r comma theta. So instead of recording a horizontal and vertical coordinate, I'm recording the distance and direction. And it turns out that every point on the coordinate plane, rectangularly speaking, can be mapped to the polar coordinate plane as well. So this sort of measurement would be more valuable for someone, doing some sort of surveying, or if you're maybe like a boat at sea, or if you're, following some sort of trajectory. You can do all sorts of different stuff, where at times a rectangular coordinate system is actually more work to work in, because it's just a little bit more cumbersome based off of the information I'm dealing with. So polar coordinates are ordered pair representing the distance and angle a point is at. So r comma theta, so it's the radius, so to speak, which kind of makes sense because it's based on all these circles that you kind of see here. And theta being the angle between that line for the distance, the ray, the vector, if you want to think about it that way, and the polar axis. So the pole is our name for the origin. So 0, 0, or actually 0, any theta would land me right smack dab at the origin here, called the pole. So you could think about this: what if I was looking at planet Earth directly from above the North Pole, P-O-L-E, pole, right? All of the longitudes and latitudes would look something like this from kind of like this top-down perspective. So pole. And the polar axis is the horizontal ray directed to the right. It's essentially the positive x-axis. All right, so here's my polar axis, like so. All right, so that's kind of the idea. Now, it turns out for polar coordinates, we will be working with both degrees or radians representing theta. So, for instance, this would be 0 degrees, or actually, let me pick a different color, maybe. I might even do this one. So 0 degrees would be right here. This would be 90 degrees, as you would suspect. Here would be 180 degrees, and this would be like 270. And then 360 would be coming back around with the 0 there. So what do you suspect that this angle is? Yeah, this is my 45 degree right there. And notice that 45 is not cut in half. It's cut into thirds. So what must this angle be? 15 degrees. Ooh, touche. And this one would be 30. Okay, so 30. Then this must be 60 and 75, I believe. Yep. And then you could find the other ones, still use some of your reference angle skills if you wanted to try to figure it out. But the angle is still always going, I'm not going to rewrite these in terms of reference angles per se. But you'd figure it out kind of like that. So let's talk about radians for these. So this would be 0 radians, right? That's not necessarily the best color. A little darker here, maybe. Like that. There we go. So there's 0 radians. This is... Oop. Writing tablet died on me. Here we go. So this is the same as pi, pi, plain old pi, vanilla pi. And 90 degrees is the same as pi over 2. So this angle here must be half of pi over 2, which is pi over 4. Right, and you guys are familiar with all these, so then this must have been pi over 6, is that right? Yeah, so then this must have been pi over 3, is that right? Yeah. No, pi over 3 would be up here, I think. Pi over 5. Wait a minute. My mind's messing up with fractions. If this is, let's see, wait a minute. This is pi over 12, I apologize, right? Because this is 1/3 of pi over 4. 1/3 of pi over 4 is pi over 12. There we go. And then 2 times pi over 12, this is pi over 6. My apologies, friends. And let's see, what would this be here? So this is 60 degrees, that would be 2 of these. This would be the pi over 3. And pi over 12, this would be 6 pi over 12, I believe. So this must have been 5 pi over 12 here, I think, something like that. But anyways, you guys get the idea. You could figure out some of this stuff. So for instance, let's see. This is 30 degrees more than 180, so this is 210. Or it's pi over 6 more than pi, or 7 pi over 6. Right, so just to get some practice with that idea. What's 270 in radians?
3 pi over 4.
3 pi over 2. 3 pi over 4 would be over here, because 3 pi over 4 is less than a full pi. So, so that would be there. 3 pi over 2, because here's pi over 2, and I've got 1, 2, and 3 of those pi over 2s. So let's see, what would this angle be in radians? Let's see, it's going to be pi over 4 more than that. So this is 6 pi over 4. So this must be 7 pi over 4, is it? You guys agree? Am I wrong? Yeah, because 8 pi over 4 would land me back at 360 degrees, or 2 pi, as I'm sure you guys remember. So I'm not going to go through all of those, but I just wanted to remind you some of that stuff, so we'd be golden. So let's talk about plotting some of these points, or graphing some of these points here, just so we can get used to the idea. Let's do some example. Oh, I'm in the blue color here. Get my pen in the inkwell here. Graph. And that looks like 360 degrees, but you're wrong, friend. That's 3, 60 degrees. That's right. That's right. So let's graph this. So what's R? What's theta?
R is 3.
R is the 3, and theta is the 60. So it's actually up to you which you reference first, I suppose. So 60 degrees, I believe, was that this one here, I think? Right. So I could go out 1, 2, 3 units and then rotate at 60 degrees and land here. Or I could just try to figure out, like, where's my 60 degree angle and then go out 3 units from there. All right, so whichever way you kind of think about that. But here's my point right there, and that is 3, 60 degrees. Right, so if I wanted 5, 60 degrees, that would be like right there. Or if I wanted -1, 60 degrees, where do you think that would be? Here's 3, here's 2, here's 1. here's 0, it actually would be right here. So it's actually possible to have points like that. -1, 60 degrees is. So it's kind of weird representing them with a negative r value, but you can. So that's the idea. Let's try one with radians. Radians, radicals. There we are. So if I want to graph 6 comma 7 pi over 6, so we've got to try to sort out where this 7 pi over 6 guy is hiding on our grid. Well, I guess it's not a grid so much anymore, isn't it? The polar plane, as some might call it. So 7 pi over 6 is more than 1 pi, right? Because 7 is bigger than 6. So here's pi. So 7 pi over 6. Pi over 6 is, I believe, this right here. 30-degree angle, more than that. So 7 pi over 6 is something like this. And I go out 6 units. So 1, 2, 3, 4, 5, 6. This could have been the same as if I plotted the point -6 comma pi over 6. Because right here's pi over 6, so if I'm talking about this angle, and instead of moving out 6 in the positive direction, I'm counting backwards 6 and would land there as well. So yeah, it is possible to represent these polar coordinates in multiple forms as a result. And not only can the radius, the little r value that they've been calling it, have a negative value, but so can too the theta that we've got, my angle. It's a terrible E there, but that's fine. I'm going to keep it. So let's graph -2, -135. So to graph this, we've got, let's see, -2, I don't have to go out too far for that one. Polar coordinates make me feel like some sort of submarine commander or something. Here we are. So -135 degrees, where's that at? Right here. Oh, and actually I happen to be 2 out in that direction as well. I didn't plan that all that intentionally, but it seems to line up. So here's a -135 degree angle and 2 units out. Right, so polar coordinates, friends, they're not that scary, and it turns out that there is a 1-to-1 correlation between the rectangular coordinate system and the polar coordinate system. We'll talk about conversions between the two a little bit later, yeah, in case you ever have to. You can probably bet that it's related somewhat to triangles and trigonometry. And I bet there's a little bit of a tangent in there, too.
But you're wrong.
Oh, okay. Well, I'm not a gambling man. So let's see, multiple representations of r comma theta. You probably don't have to write down all the words. Even if you just write down these 2 things, you might be good. It says if P has polar coordinates r comma theta, then P can also be represented by polar coordinates r comma theta plus or minus 2 pi k, which adding 2 pi k to that, what's 2 pi k? Where k is an integer. That's important. That's like adding or subtracting multiples of 360 degrees. Okay. And then this one's a little bit trickier to find. Or it could be listed as the opposite of r. and theta is going to be adding some multiple of pi to that. But specifically, not any multiple, not ones that land on 360 or 720, but ones that land on like 180 or 540. 2k plus 1 you might recognize as the mathematical definition of an odd number when k is an integer. So I'm adding odd multiples of pi, or odd multiples of 180, which is going to land me on that point as well. So let me actually, maybe I'll even grab a little grid here. Just to make this point a little clearer. So if I have this point here, let's say, so that's 5 comma 45 degrees. All right. I could have also found that point by adding any number of 360s to it, right? So that's kind of like coterminal angles is essentially all this is. Or if I add an odd multiple of pi, or 180 to it, and then have a negative r value, that would bring me right back to the same location. Okay? Is the idea. But if I added a full 360 and had a negative r value, I'd be landing in the opposite spot. And that's why this has to be an odd multiple of 180s there. I'll leave that there. Bam. Good. Good, good, good. So now plotting points, you might be like, wow, this ain't that bad. Maybe. But remember, with rectangular coordinates, we never just stopped at plotting points. We got to the point of graphing equations. Yes. Yes. We didn't. But you don't have to write them down right now. So it says polar equation is an equation expressed in the form of polar coordinates. So I'll throw some examples there. That might be like r equals 7, or theta equals 20 degrees, or maybe even some combination r equals 3 theta, or 3 theta squared. So you could actually have all sorts of crazy equations related to this stuff, and then end up graphing those as a result. And a polar graph is the set of all points whose coordinates r comma theta satisfy the given polar equation. So if I have this, I'm then interested in what are the infinitely many combinations of r and theta that make that equation true, and that's what I would be talking about. So let's do an example of a couple of these graphs. Let's graph r equals 3. So r equals a number graph. All right, so think about the radius is the constant. Radius is constant here. So what do you think this graph is going to look like? What's the set of all points where the radius is 3? So think about these points. So that would be like 3 and 0 degrees. That would be like 3 and 45 degrees, or 3 and negative 90 degrees, or 3 and 135. Oh yeah, if I plot all of the points, I think you'd agree that all of the points, this circle's getting ugly. Whoa. There we go. It would represent a circle, right? Because theta could have been anything according to this. And that is what we would have. So a circle is actually, in polar equation speak, r equals a number is the equation of a circle. Which I'd like to point out is, well, a circle centered about the pole, or the origin. Which notice is a little easier than this, which is what the equation of a circle was in rectangular form. So yeah, so this is a circle. Good stuff. Circle with radius 3. And actually, another way I could write the equation of the circle is r equals negative 3. Would technically also work. Except this would be the point negative 3 comma 0. Right? And it would just like plot it backwards. This would be negative 345, and this would be negative 390. because it would be like this angle and opposite. So crazy stuff like that can happen. Cray. Let's do, oh, here's a good graph. I like it a lot. So what if I have an example where I want to graph theta equals something? Theta. So this is all possible r comma theta representations in which we happen to have theta equal to 3 pi over 4. A line, he says. There's not many, well, I guess there's some lines on this graph. There's lots of circles and lines. I suppose that would make sense that the simplest types of graphs that this system would be efficient at making are circles and lines. So let's see, 3 pi over 4 is this angle here, right? So here's 3 pi over 4 comma 2. Here's 3 pi over 4 comma 4. Here's 3 pi over 4 comma 0. Here's 3 pi over 4 comma 5, right? And if I plot all of the points that make that true, it's a line that passes through the pole, or not.
Why does it go on the right side as well? Because that's not 3 pi over 4.
Well, this would be 3 pi over 4 negative 5. Maybe I didn't specify.
Oh, going from the x-axis on the left.
Well, it's still a positive 3 pi over 4, but instead of 1, 2, 3, 4, 5, I'm going negative 1, negative 2, negative 3, negative 4, negative 5 to get there. So you can have negative r values like that. So all possible r values that have a theta at 3 pi over 4 gives me the equation of a line. So it's a line through.
Negative 5 is greater than? What is negative 5 again?
Oh, I just picked a point there. Yeah. So like this would be negative 7 3 pi over 4. This would be 0 3 pi over 4. 8 3 pi over 4. Yeah, I was just indicating that you could have that happen. So it's a line through the pole at angle theta. Okay, so that's interesting. So there's two basic equations for us to start with. And the last thing I want to show you is the distance formula. Actually, I'm going to start with a graph and kind of semi-justify the distance formula for us first. Yeah, we're good at this. We got this. All right, distance formula in the rectangular coordinate system was all based on, yeah. The little derivation I'm doing here you won't have to write down. But in the rectangular coordinate system was all based on our x and y values, horizontal and verticals, and we actually kind of broke it into a right triangle, and it was distance formula was just Pythagorean theorem. Let's look at this. So if I had, say, this point, 6 at 135, like that, and let's say I had this point here, maybe 3 at 45, no, I don't want it to land on a 3 at 30 degrees. Okay? And I wanted to find the distance between these 2 points. I'll actually even put that in a fancier color. So this is the distance that I want to find. Now this is not necessarily going to be a right triangle, and in this case I made it so it wasn't. But let's label what we do know. So here would be, this point would be, say, like r2 comma theta 2. And this would be, actually, do I want it that way? No, we'll label this 1, 1. r1 comma theta 1. And this would be like r2 comma d2. I mean theta 2. StarCraft. I mean Star Wars. StarCraft is the video game I like. Man. Star Trek, StarCraft, Star Wars, seriously. Too many of them to keep track of. So here's, what is this angle here? Well, yeah, 30 degrees in this case, or theta 1, generically speaking. Yeah, I agree with you. You're right. You're right. And what is this angle here, generically speaking? This is theta 2 degrees. So the angle of just this inside of the triangle, what would that angle be? Theta 2 minus theta 1. Right? Do you guys agree? Or theta 1 plus this green angle would equal the red angle. So that's this interior angle. These blue distances, this is R1 and R2. So the distance between these 2 points is this purple line segment, right? Is actually the missing side of a triangle, and I kind of can do a law of cosines problem with this.
Oh. You don't need to know long cosines. Really not necessary.
So the distance squared would equal R1 squared plus R2 squared minus 2 times R1 R2 times cosine of my angle, which is theta 2 minus theta 1. And if I solve that for the distance, the formula looks a little something like this. Yeah. So the difference between this and this down here is they just rooted both sides, and they only took the positive square root. So yeah, distance formula in the polar plane is if you have point 1 and point 2, 2 points in the polar plane, then the distance between those two is the square root of, it's just straight up law of cosines there. And the only tricky part to that was the fact that you had to find this little angle in between. So I'm not going to show an example on how to do that. It's just a matter of plugging in r's and thetas, and you find the distance like so. So we'll call it a day. Thanks for watching, Internet friends. Bye-bye.